And again, I draw the picture. Did you guys come up with something close to that, hopefully?
Yeah.
Right? And these are the numbers blended learning wants to see. If you get them wrong because of rounding, always let me know and I'll correct them in the blended learning. But that's why we want to give them to you as blended learning wants them. And so, if my bandwidth, too big of a number to write, but if my bandwidth is 265,290 wide, and the middle was 2,056,000, could you calculate where F1 and F2 are? We can look at the formulas, but look at it. It's basically resonant frequency minus half of the bandwidth, or resonant frequency plus half of the bandwidth. I find when I put in picture format, it makes it easier to see. Those are the numbers we should have. And if you want to know where these relate, these come in as I don't want to put Q. Just have your little sketch and you'll see the questions as they come up when they're asking for those things right there. Okay? At resonance, this is my true power. What's the relationship between true power and apparent power at resonance?
Should be equal, right?
Should be equal, isn't it? The current's the same, the ohms are the same, I squared ohms, I squared ohms is the same. E times I, E there, I here, E times I should be the same at resonance. What would my power factor be at resonance? 1 or 100%, right? We call that unity sometimes, at unity. So it should be 100%. What should my phase angle be? 0, right? Isn't it a flat triangle? It's neither pointing up nor is it pointing down. It's flat. Okay. So those are some of the questions we're going to get in on that. And if we took because of time, I'm gonna jump ahead here. But if I basically redrew that circuit with the same inductor, 60, remember, microhertz, and 100 picofarads, at a new frequency, either F1 or F2, would my XL and my XC change? Yeah, one would be longer, one would be shorter. I'd generate a difference, wouldn't I? I'd generate a difference. And if I generate that difference, my Z starts increasing, all the numbers change. So at half power point 1 and half power point 2, where do you think, with that increase and that decrease in frequency, where do you think my true power would be at half power point 1 or half power point 2? Half of that. About 28 plus or minus, right? About half of 56. So the best application I can give you is that concept of tuning a radio. Because when you tune that radio, there's a little bit of range where you can still hear it just fine, right? You bump it a little bit, it's still fine. You bump it a little the other way, it's still fine. But if you go too far, you've gone outside of the range. That's what I want to think of with half power points. Okay? So let's just talk about zero frequency and infinite frequency for a second. Then I'll hand out a form to you. And for that, I'm going to decrease some, get rid of some of these numbers because they change. We still put the same voltage on there. Still have that. Just think of these conceptually. If we go zero frequency, that's no longer a resonance, but 0 hertz is like a battery, isn't that right? Doesn't the battery put out power? It's just DC, it's only going one direction. Because hertz means how many times does it oscillate. And if it's 0 times, that means it stays positive, this direction, or it stays negative, this direction. It only goes one direction. I put a battery in. Just want to ask you, what do you think happens to current flow in this circuit at 0 hertz? Effectively, DC power. DC current flow. I put a battery in there. What happens to, how much current flow do I get? 0. Why? Because in the middle of the capacitor, isn't there a dielectric in there, an insulator? So yeah, at first the current goes and it stacks up here and it gets rid of current here. But as soon as it charges up the capacitor, what does it do? It just sits. So where's all the voltage going to be? If I do put a battery on here with 75 volts, leave it just long enough to charge up, right? There's no current flowing through here. So is there any voltage drop? Can't be if there's no current. No current flowing here, no voltage drop. But do I have a charge across this? What would the voltage be there on the capacitor?
75 volts. Be the whole thing.
Yeah, because it pushed with 75 volts worth of pressure, and it's going to push on this thing, and it's going to keep pushing electrons until, and kicking them off of this side, sucking them back up here, until this thing has an equal and opposite charge, and they start pushing against each other. Right? It's just like charging a battery up in your house. Do you notice that if you have a dead battery and you put it on a battery charger, it draws a lot of amps? Because it's empty, and the battery has no pushback on you. So it just says, give me all the amps. But as the battery starts charging up, does the rate of charge slow down? And then at the very end, we just put a trickle charge to keep it up in there, because the battery now has a charge on it and it's pushing back. So if I'm pushing 14 volts at my car battery and it's got nothing, I'm pushing a lot of current. But as it charges up and it's about 13 volts now, and I'm pushing with 14, there's only a difference of 1 volt, so its push is not as much. That's why we talk of trickle charge, just to keep something charged up. Where it drops off, we're like, well, there you go, a little more. Okay? Yeah. So DC power, no current flow. I have a voltage drop across here, and that's about it. And that's going to affect my numbers through it all. How about if I did equally impossible to do, infinite hertz? And for what I got to think there is, what happens to an inductor at infinite hertz?
It'll be infinitely large.
Infinitely large, and XL is measured in ohms. So that thing is constantly changing so fast. And what do inductors oppose? Changes in current. And if that change is infinitely large, it's just a total opposition to it. It won't let anything through. Because it's delaying it on the way up, but it's already immediately on the bottom, and it's delaying it on the way the other way. So it's a theoretical concept, but it's got infinite ohms. So it doesn't let any current through it. What does a capacitor do at infinite? The denominator gets as big as possible, right? So if I've got millions and billions and trillions down here, with 1 over, I got nothing. That's basically a short circuit. It's just, you know, I get 1 electron here and I'm already taking it away and putting it on the other side. Can't build up a charge on it. So, theoretical, and we basically have to look at our formulas and go, wait a minute, that would block all current at infinite. So I wouldn't get any power across this. My bandwidth is the range between my half power on the resistor, half power on the resistor the other way, right? Lower frequencies, going to be more capacitive. Higher frequencies, going to be more inductive. Okay, that comes down. And as I get lower and lower frequencies, no current flows. Lower and lower, no current flows here. Just a guess. Do you think it's going to be opposite or the same in parallel? It's all opposite because we got a parallel, if you will. We have no current at resonance or minimal current at resonance, and peak on the other. But we'll get into that in a little bit. Okay, so there's my series take on it. So here, my friends, is your. This is you were talking about slave labor earlier. This is slave labor, the data entry. Here's a chart for you. And I added 2 extra lines to the chart. And the reason I added them is occasionally we get mathematical purists coming through here. Okay? When you get this chart, take a look at it. And my half PowerPoints, F1 and F2, right? These numbers are written as your blended learning should take them for rounding issues, right? So these numbers relate to that quiz you were talking about, Chris. And this is the form where it says, email me when you're done, and then you'll get something. This is what you get, right? This is basically the bulk of the answers, however many of them. All these questions, 7 to 13, 18, and 20 to 91. Leaves you about 20 questions in that whole lesson. Some of which we've gone over, right? Some are the bandwidth, the Q, F2, F1, some of those other numbers, right? Some of those are those questions in there. So we've done the bulk of that lesson here between that and this sheet. But look here, if you will. You see resonant frequency down the middle. Now go to F1 and F2. What happens to XL and XC relative to each other on F1 and F2? Round the numbers off. Do they kind of flop places? At F1, XL is 725, XC is 825. And they're the opposite at F2. Do you see how that works? That means there's a difference of 100 up here when it's inductive, and the difference is 100 down here when it's capacitive. It's just whether it's up or whether it's down. Okay? And that's why I added 2 lines. Blended learning just had you going 1.7 and 1.9. I added the 3.3 and the 10. Because if you go to infinite and 0, you see they're opposite each other there. But the corollary, if you will, for 0.3 is 3 times as much, 3.3 times as much. The corollary for 0.1, 1/10, is 10 times as much. Blended learning did 1.9, which mathematically isn't pure. What that means, if you're into math, what that means is this. The chart is not like this, equal on both sides, right? The chart is more like this, where it kind of layers off like that. It's whatever we call logarithmic. Did you guys look at your overcurrent, time current curves? Have you guys seen those yet in a safety class? Time current curves? I know next quarter you study them in detail. Sometimes you see them. But that's basically what it means. It's not a symmetrical chart, but blended learning treats it as if it is. So I put those lines on for the purists, because you see, basically it means XL and XC change places. It becomes more inductive, more capacitive, both on the voltage drops. And you see how your power drops off? Your resistor's power, your true power drops off either side. Yeah, keeps going down. So those are the answers there. That's the series. The other thing I want to hand out is this guy. Let me just put this on the table. Comparisons between them, right? This is, and I started the printer full size before, and then I'm like, man, I should have done half size. But this is the last PowerPoint that you had with AC4, but it goes over the nuts and bolts of this concept for series and parallel circuits, right? And I told you that lesson 8 was really going to play into this class. So this is a handout worth having, worth seeing if you can understand why those things are the case. Did I give everyone one? Yeah. So if there's anything on this little handout that you don't get, make sure to ask me next week before the test, Because it's that, when do we have minimum, when do we have maximum? That's gonna be important. So let me ask you with series, let me ask you again with series. When do I have, or at resonance with series, at resonance, current and impedance. And we're looking at total values, current and impedance. Which is min, which is max at resonance? Think about that for a second. See if you got it sorted out. Think about it. Z and I. Which is min, which is max at resonance? Just think about it for a second. I'll tell you on this chart, but think if you can get your reasoning down.
Current's gonna be at its maximum and impedance will be at minimum.
C would be the min.
Z would be min. Isn't this a picture of this at resonance? Z equals R. These guys cancel out. They act like a short circuit. It seems as though it's purely resistive circuit. Z is at its minimum. I mean, sorry, max, minimum. So current has to be at its maximum. So we need a way to help us remember that. Sometimes we just memorize. If a picture can help us, at resonant frequency. Okay. That's a series concept. Okay. I'm just going to briefly do a parallel to get the picture of the opposite. I'll do it picture format, and then we have blended learning kind of walks us through a bunch of questions to make us see this as well. But if I go picture format with a series RLC circuit, at resonant frequency, we're looking at Z, which is the total circuit value, and IT. We're wondering which is minimum and maximum. So at resonant frequency, what equals what? XL. Is that right? XL equals XC. If those two equal each other, what do the currents do? Isn't it? If I have the same ohms here and the same ohms here, am I going to have the same current? Yeah, because it's whatever voltage is pushing down there. It's the same voltage. So if these currents equal each other, 10 amps, 10 amps, how many amps do I read here? 10 amps going back and forward. How many amps do I read here? I'm gonna go with 0.
0, sorry.
Yeah, do you see why?
I was
Yeah.
getting confused with the two 10s right next to each other.
Yeah, because that 10 and this 10, while one is negative, this one's positive.
Yeah.
And then when this switches to negative, that one becomes positive. They're feeding each other. Those are my vectors. They cancel each other out, don't they? And so the circuit just needs to provide for the R. Is there anything that can get rid of this need for the R? Or does it have to keep feeding the resistor? Can I use anything to compensate for the resistor? Not for the resistor. The capacitor is only going to complement the inductor. Because remember, the capacitor and the inductor's currents go opposite each other, they'll complement. But the resistor, there's nothing. Whatever I end up here gets added Pythagoreanly with the resistor. So it's always got to provide this. But when these two are perfectly balanced, it doesn't need to kick in anything here. When they're not balanced, it needs to kick in the difference. So right now, am I at minimum current or maximum since I'm resonant? What's it?
Maximum?
Current?
Minimum,
Minimum.
Why do you say minimum, Megan?
opposite of series.
Yeah, opposite of series, that's good. That's one way to do it. I'm with you.
You only have to provide for one part of the.
The source needs to provide for the resistance, and it needs to continually provide for that resistance. But if I can get this to balance this, they cancel each other out. And my total current equals my IR. The only thing I can do to reduce this less than 10 amps is pull a resistor out of the circuit. That's the only way I can reduce it. So right now it's at minimum current, because if I move away from resonance, XL and XC become different, that means the currents become different. That means that the smaller amount goes back and forward, but the source would need to kick in something, and then the source would need to provide for the resistor plus the difference here. Vectorially, of course. Okay. If I'm at minimum current, what does that have to mean for my ohms? Maximum. Inverse relationship between current and ohms. And the half power points here, look on the back page of that handout I just gave you. It has the two charts, the PowerPoint one. Look on the very last page. And there should be the two. I do them with current on the vertical column and frequency on the bottom. You see how the one with the big lettering on it? Yeah, that one, last page. The series parallel, big letter one. You see how those two charts are opposite each other? At resonant frequency, parallel is zero current. Zero would be if I didn't have a resistor. Minimum is, I'm assuming I have a resistance of sorts, so it's the minimum amount of current there. So we still have half power points on that as well. Okay. Not going to get into calculation of that, but we have those there. And here is the 10 amps. That's just for the IR. So it's the least I can get in that circuit, that particular circuit. Change in frequencies, it can only go more than 10 amps. Never go less. Okay. See how we're opposite? And what Mark calls that, he calls it the parallel. So that helps you remember that parallel is a well. Zero current. As long as you remember you're looking at current there. Or you remember your vectors here, it's the lowest ohms at impedance, right? Come up with your system that works for you. And we'll start out with a couple exercises on that next week. Okay. Curiosities on that, or you think, do we have enough tools at least to go with to work?